All right, we're gonna get started. This is the last video for cardiology. We're gonna talk about blood composition. We're gonna talk about what's in the plasma, red blood cells, what's in your white portion, or like the buffy portion of your liquid of blood. We're talking about red blood cells, how they get broken down, what happens to hemoglobin, and then heme, and then the iron. We're gonna talk about hemostasis, which is maintaining like blood flow within the thing and preventing blood loss. Talk about the different things that deal with that, and we're going to talk about what ends the clots and the coagulation within creating clots with platelets. Great. Okay, so we're going to get started with, here's my blue marker. We like the blue marker. We're going to get started with blood composition. If you were to fill up a test tube with your blood and let it sit for a while, you'd get 3 different portions. So this upper portion is the plasma. Down here are your red blood cells, and these is where your white blood cells are. White blood cells. Okay. So your plasma makes up about 55% of your blood, and a large portion of that is water. The other portions of it is you've got several proteins. You've got albumin, you've got platelets, which are cell fragments from cells called megakaryocytes. Those are made within your bone marrow, and the megakaryocytes break down and turn into these what's called denucleated cell fragments, and that's your platelets. Also contains fibrinogen, which we'll talk about more when we get to hemostasis. And it also has many antibodies useful for fighting infection. But that's more immunology stuff. Okay, so that's our major composition of blood. So 55% plasma, majority of it is just water, and then these are the other parts. Your red blood cells make up for around the other 40-45-ish%. And those are your red blood cells, which, look. Nah, that's not a great drawing. We'll try again. There you go. Kind of like little donut shapes, but you haven't poked the hole all the way through. And then your white blood cells, those are largely your immune system. One of the more important ones that we'll talk about is the macrophages. Red blood cells live. They're living cells. They live for only around 120 days. And so after the red blood cells have degraded, there's some kind of way to recycle them. And so macrophages, one of the types of white blood cells, also get made in your bone marrow. They will come along and they will kind of like eat the red blood cell and degrade it and break it down into parts that are able to be reused again. So let's talk about what heme is. So in your red blood cell, we're going to draw a big one. Great, there is a big red blood cell. And you've got around, I don't remember the number, but each day you are losing about 1 to 2 million of these. So you got to make a whole bunch. So that's how much your bone marrow is producing. What makes it even more interesting, so inside, this is not drawn to scale. Okay. So hemoglobin, which is what this is made up of 8 different parts. It has alpha subunits, and it has beta subunits. And attached to each of these units, this little blue dot that I have circled there, that is what's called heme. And so heme has an interesting structure. I'm going to attempt to draw it but if you don't like it, that's totally okay. Oh, that's a hexagon. Wait, no, it's not. 1, 2, 3, 4, 5. Cool. That's nitrogen. There's some double bonds in here, but this is kind of like the general chemical structure of hemoglobin. And so this iron sitting right here has a positive 2 charge, and so that will attract oxygen, which kind of will have a negative charge on it. And so we'll pull it in and it will hold it. So one heme can hold one set of oxygen, and so that's 4 oxygens per hemoglobin. Each red blood cell has around 1 point something million hemoglobin, and you've got a ton of hemoglobin, and you've got a lot of red blood cells that are getting broken down by those macrophages. And so makes sense, we're going to want to figure out some way that we can recycle this. So we'll talk about the iron first. That is significantly easier to break down and be used. So the thing that's used, it's stored in the liver, and so it is brought, so this is broken down. You've got heme and iron. The iron is picked up by a protein called transferritin, and it is brought into the liver through the blood, and it is stored with a protein called fibrin. And then when it's needed to be used to make more red blood cells, it's picked up again by transferritin and then circulated through the blood until it gets to where it needs to go. Heme, on the other hand, is a little more annoying to try to deal with. We don't have any good ways to quickly break it down. So we have a really fun cascade or pathway that we use to get rid of heme. So we're going to start with heme. Heme is then broken down into what's called biliverdin. Biliverdin has a characteristic like green-blue color, and this is a polar molecule, so it can't really pass through membranes. And then what happens is biliverdin kind of folds in on itself because it's got some single bonds that can rotate. And so biliverdin will fold in on itself, and after interacting with an enzyme, it turns into what's called bilirubin. Bilirubin. I'm not entirely sure if there's only one L or two L's. I've seen it many different both ways. So bilirubin is kind of annoying, and we're going to make a little note here. Yellow color. So this is super important. So bilirubin, because it's folded in on itself, it's hiding all of its polarity. And so what happens is this allows it to freely pass through cell membranes and through the epithelial layers of blood vessels. So it can end up in interstitial space. And if you have something like a consistent high blood pressure, or maybe some kind of like cut, or something where like your liver isn't working, I'll explain that one later. Bilirubin can like build up within your interstitial space, and it will build up in some kind of yellow color, and that's what we have as jaundice. Bilirubin is picked up by albumin, and your liver makes albumin, so that's why it's really important that you have a healthy liver, because we want a lot of albumin to pick up this bilirubin, and that brings it to the liver. And at the liver sticks glucuronic acid on it. Glucuronic acid. And so that makes it polar again. This now can't pass through membranes freely. The liver will stick it into the bile duct. Actually, once glucuronic acid is stuck on it, it's called conjugated. conjugated bilirubin. So conjugated bilirubin is then stuck into the bile duct. We're going to write right here, bile duct. So it's put in the bile duct and then plugged into the intestines, where it gets eaten by bacteria. Bile duct first, and then eaten by bacteria. When it gets eaten by bacteria, it is then converted into what's called urobilinogen. And so urobilinogen can go one of two ways. So 50% of the time, it's going to be kind of like uptaken by the intestines, put into the bloodstream, and then it's going to circulate to the kidneys. The kidneys are going to turn it into urobilin, which interestingly enough has a yellow color. And so this is then peed out through ureters and urethras. Or if it's not, absorbed by the intestines, it stays within the intestines and is converted into stercobilin. And so this has a brown color. Fun fact, this is then excreted out through the anus. And that's your fecal matter. So that's how we get rid of heme. We can't reuse it, really. So our body provides some kind of way to convert it into something that can become water soluble and dumped out of our system. Okay. Now I'm going to talk about hemostasis. So I'm going to draw a blood vessel. Draw this through that. Great. Okay. Each of these are endothelial cells or squamous cells. This pink stuff, that's collagen fibers that helps hold things together within our body. Really important. So normally within the blood, we have these platelets. I'm going to draw fun little platelet. Great. So on platelets, we have on them what is called a VWF receptor. And so what that means, so it is also known as a Van Willebrand factor receptor. Can you see that? Not super well. Okay, I'm going to draw it over here instead because of the glare. That's fine. Yeah, so we'll draw it over here. So here's our platelet. Doesn't really look like anything special, and it's got this receptor. And so these epithelial cells and these squamous cells are constantly releasing these little things, which are called VWF, or Van Willebrand factor. And so if one of them binds to a platelet, nothing happens. Nothing interesting. But what can happen is, say you get some kind of cut. And so now you've got a hole in our epithelial cells, but the collagen is still there. And so collagen has a overall minus charge called the negative zeta potential. And so what will happen is you can get these Van Willebrand factors. I'm going to use a different color to describe them now. We're going to use black. So they'll stick here. So here's our Van Willebrand factors. And you can get a platelet to bind to them. I'm not going to draw the receptor. It's just assumed that that's what's binding here. And so it binds here. As blood is flowing by, the platelet is going to be moved. And so what the Van Willebrand factor receptor is it's a mechanoreceptor. So when the platelet is moved along by the rest of the blood flowing, that receptor opens, and that causes the platelet to go through a change. So it's going to turn into kind of a more interesting shape. And so within, we're going to draw, oh boy. Okay, so we're going to draw that. And we're going to draw little pink dots. Okay, so these black dots inside that, you can still see those? Great. So those are what's called dense granules. And so your dense granules inside the platelet, they contain calcium, ADP, and they contain factor 8 and factor 5. That is important for our cascades. We'll get there in a second. Our little pink dots, those are called alpha granules. And those contain what's called XIII, or otherwise known as thromboxane. Okay, so those are granules. I'm going to erase that so I have space. So what happens is those will release that stuff. And so on each platelet, they also have receptors for the ADP, and they have receptors for the thromboxane, or the XIII. And so those will bind, and those will start becoming their fun, interesting shape. And so you'll start getting this buildup of platelets that have this funny shape because of that release from the starting platelet. So what happens, and just important note is calcium is required for platelets to activate and they can go either of the way of using the Van Willebrand factor, they can use thromboxane, they can use ADP. So they've got several ways of the platelet starting to activate. And if you remember when I talked about the components of plasma, one of the proteins in there is called fibrinogen. And so platelets also have receptors for this fibrinogen. And so fibrinogen comes along, here's our receptor. We're going to draw another receptor here, receptor here, receptor here. If you notice what I'm doing with these, you can already start to guess what's going to happen. So fibrinogen is going to come along. I'm going to use black. And it's going to bind to one receptor, and then it's going to catch another platelet. And so you're going to get this big chain and this like huge aggregation of platelets. And so this is our platelet aggregation. So platelet will become activated by any of those three pathways, and the fibrinogen is going to bind to those receptors, and it's going to bind to another receptor from other platelets, and you're going to start getting this big clump of platelets that's going to build up around this area where blood was trying to flow out. Okay. The next thing that happens. Out here, we've got our negative zeta potential. I'm going to draw this further out. I'm not going to draw what's happening. Yeah, okay. Remember. Okay, I'm going to draw our collagen. Okay, so here's our platelet aggregation. Oh my god, I'm getting so many texts from people. Okay, so now we're going to talk about the cascades. So this is really important. So fibrinogen will eventually turn into fibrin, and that's where you start getting like fiber like production within this area to start. These will start releasing proteins and factors that will cause our epithelial cells to start dividing and start growing to start healing this wound. And so this cascade will help do that. So really interesting numbering scheme. Don't worry about it. So if you remember, we've got this negative zeta potential out here for the collagen. And so we have what's called factor 12, not 13, not yet. So factor 12 is going to bump and interact with the collagen, and then it's going to turn into 12A. And the A just means activated. And so just so you know that this is our intrinsic pathway. So 12 is then going to interact with factor 13. And it's going to turn into 13A. Oh, just kidding, not 13. It's going to interact with 11. 11A, sorry. 11A. Then we have 9A. Well, 9 is going to interact with 11 and turn into 9A. And then 9A has to work with factor 8, which is released from platelets. They're dense granules. And then I'm going to remove that, okay? And then we have factor, not 5, but 10. 10 is going to interact with 9A and the 8 cofactor and turn into 10A. And then plus our cofactor 5, which is also released from those dense granules. It's going to interact with factor 2, which will turn into 2A. Again, the A stands for activated. This will then interact with factor 1. This is actually going to use a different color now. We'll use green. So this is known as prothrombin. And after it's activated, it's known as just thrombin. Right here, you'll recognize this name. This is known as fibrinogen. And this is known as fibrin. So, hope you can appreciate this cascade. One of these can interact with maybe 1,000 of these, and then one of those will interact with maybe 1,000 of these, one of those, 1,000 of these, one of those, 1,000 of these. So you'll start with a small amount, but because it's a cascade, you can get this massive, massive amount of stuff and a ton of fibrin being produced. When you introduce fibrin into this, you start creating those, you start seeing scabs for any kind of external wounds, and you'll start getting platelet-derived growth factors. So that's what increases your epithelial cells from growing and starting that healing process. Fibrin will make like a giant kind of like web and net around the injury. So this is our intrinsic pathway. Interestingly enough, there is a second pathway, and this is called the extrinsic pathway. So I'm going to draw it right here. I'm going to erase our platelets, so don't mind me. This one isn't nearly as bad. So say we've got sign of wound here. The cells out here within your tissue and in the interstitial space, they release, I'm going to do this in a different color. We'll do red, why not? So out here, they're releasing what's called factor 3. I'm going to erase that collagen just so I can show it. So we have within the blood, we have factor 7. When factor 7 interacts with factor 3, no, that's not 7. It becomes 7A. 7A will then interact with, I don't remember this one. Pretty sure it's 13. Nope, no it's not. Yeah, it is. Going to interact with 13, turn it into 13A. That feels wrong. Is it 6? No. You've got 12, 11, 10, 9, 8, 2, 1, 3. It's not 4. I think it is 13. And then 13 is going to interact with 10. Turn it into 10A, and then it will follow the same step that this does. Okay, I'm going to double check on that. Okay, I'm glad I'm checked. So just kidding. There is no 13. What happens is 10 will interact with 7A and turn into 10A, and then it will follow this same cascade. 10A will interact with cofactor 5, and then when 2 comes along, it's going to cleave it, turn it into factor 2A, and then 1 comes along, interacts with 2A, turns into fibrin, or 1A. Okay, and so that's our cascades. So the interesting thing is you can have some drugs that will take out one cascade, so like your extrinsic cascade. Let me write this here. Extrinsic and then intrinsic. The reason it's called intrinsic is because our starting factor is inside the blood, whereas for extrinsic our starting factor is outside of the blood. And so both of these are used to develop clots. And if you give someone kind of a drug that will take out, say, maybe factor 7, this factor, you'll lose your extrinsic cascade, but your intrinsic cascade will still be going. So it'll just take longer to develop blood clots. So those are really helpful in being blood thinners. Okay, and then ending clots. So one of the things, so we have TPA, and I don't remember exactly what the name is, but it's it's used for strokes. It's a clot buster. So it's really helpful in breaking down fibrinogen. So this will activate plasminogen. Plasminogen is a normally inert protein within the blood. And when TPA interacts with it, it will turn into plasmin. And plasmin does fibrinolysis, so it's going to break down fibrin. And so once this is healthy cells and they've completely recovered, you need some kind of way to break down this clot. And so plasmin, when it's activated, is going to come along, it's going to break down that fibrin, and then everything's going to go, it's going to be filtered out, recycled. And so that is hemostasis and ending clots. I don't think there's anything else. Yeah. That's it.